Hello there, we're going to do chapter 17, part 1. We did cover some of the names here in class already, but I wanted to remind you of them before we move on to some of the other reactions in the remaining videos. So, what's good about these is they continue our group with carbonyls. We'd already talked about the aldehydes and the ketones. The aldehydes and the ketones are groups where we only have a carbon or a hydrogen atom bonded to the carbonyl. However, when we have compounds that have an electronegative atom bonded to that carbonyl, they then change their character, reactivity, and their names. If we have an OH, it's a carboxylic acid. If we have a chloride, it's an acid chloride. If we have an OR group, then it is an ester. And if we have a nitrogen-containing compound, it's an amide. Okay. So, first and foremost, carboxylic acid derivatives are anything that contains the carboxyl group, which is a carbonyl plus an OH. The parents of the acyl groups, i.e. carboxylic acid derivative. So, if we have this acyl group or this carboxylic acid derivative and we convert it to the chloride, it's called an acyl chloride. If we have two carboxylic acids and remove one equivalent of water, we end up with what we call an acid anhydride. That's where the anhydride function comes from. If you can imagine adding water across one of those carbonyl oxygen bonds, you will end up with two carboxylic acids. If instead we remove the OH and add an OR group, that allows us to have an ester group. And then I want to move over to the right side of the page. These are the amides. If we have a nitrogen with two hydrogens on it, we consider those a primary amide. If we have a nitrogen plus an R group, that's a secondary amide. And if we have a nitrogen and two R groups, we call those tertiary amides. Notice on that top structure, that primary amide, if you remove the O and two hydrogens or remove water, you end up with the last group on the left side, which is the nitrile. Imagine removing water from the amide function to create nitrile. Okay, so when we're doing nomenclature on these things, we now get to the point where we have to figure out our priorities. We have so many different functional groups that we need to prioritize those by which functional group takes number one, number two, etc. So if we look down at the bottom of the list here, we have alkyl halides. Remember, it does not change the parent name. It's always going to be the alkane or alkyne or alkene plus the halo as a substituent. Ether functionality is also the same. It has the alkoxy as the substituent, does not change the parent name. Then we have alkanes, alkynes, and alkenes, and those change in that priority. That's how we can have the ene-ine or the ene-alls. Okay. The next one up would be the amine group, then the alcohol, ketone, and aldehyde. If we have a terminal aldehyde, the prefix name can be formyl. If the entire carbonyl group with hydrogen is pendant to the main chain, it's the formyl group. If that aldehyde is in the main chain, we can call that an oxo group. Next we have the nitriles followed by the amides, because nitriles are a dehydrated form of the amide. Then there's the ester, and then there's the carboxylic acid. Once you have the carboxylic acid, within that you can also have the carboxylic acid anhydride, carboxylic acid chloride. So those would both fall under the carboxylic acid primary name. Notice the prefix names on all of these change. So if you have two different carboxylic acids on the same main chain, one of the substituents is going to be called the carboxy group. In an ester, if that is not the main name of the chain, it's a substituent to that main chain, we're going to call that the alkoxy-carbonyl group. If we have an amide that is not part of the main chain, it's a substituent, then it's the amido group. If we have a nitrile that's not part of that main chain, we have the cyano group. And an alkoxy in the main chain, an aldehyde in the main chain is the oxo, where an aldehyde pendant to the main chain is a formyl. A ketone, either in the main chain or not, is also called oxo. In the main chain, it's an one. Outside of the main chain, it's an oxo. Or if it's a substituent, we also have the hydroxy, amino, alkenyl, alkynyl, alkyl, alkoxy, and halo substituents as such. All right, so let's talk about naming our carboxylic acids. First and foremost, we want to take the longest main chain, including the carbonyl of the carboxylic acid. So in the case of the middle compound here, we have 1, 2, 3, 4 carbons in the main chain. So it's butonic acid. We drop the A and add OIC acid. And then we talk about whatever substituents we have on the main chain. In this case, we have a methyl ether on the main chain, and so we call that the 2-methoxybutonic acid. And when we name rings, we name the ring first. So in this case, we have the cyclopentane carboxylic acid. And then we have with it the methyl group is on the main chain. So we name that the 3-methyl cyclopentane carboxylic acid. Okay? So the COO bonded to the chain, the longest chain, including the carbonyl, is going to be the oic acid. Bonded to a ring, you have the ring name plus carboxylic acid. If the number in the chain is included in that, if it's in C1, apply all the other nomenclature rules. Remember, carboxylic acid is the highest priority, so if you have one on there, you're probably going to be named for it first. Okay. Let's start out with some of the common names associated with it. The systematic name for just having a single carbonyl with a hydrogen plus one OH is methanoic acid. So it's methane, it's just the single carbon, so it'd be methane. Drop the E, add oic acid, and then we'd have ethanoic acid, propionic acid, butanoic acid, pentanoic acid, etc. But the common names are more familiar in some of the literature is formic acid, acetic acid, which is vinegar, propionic acid, butyric acid, valeric acid, both of which actually smell pretty bad. And then we have caproic acid, and of course the one with the benzene directly bonded to the carbonyl is called benzoic acid or benzene carboxylic acid. Okay, and those have different reasons for being called that way. Okay, once we get up to 2 acids on there, we can name them as a number of different common names, or systematically you would take the longest chain, including the ones with the carbonyls, and in the case of the one on the left here, we have 2 carbons in the total chain, so that means it's ethane, and we drop the end and we add dioic acid since we have a diacid. So it's ethane dioic acid. In the next one in the middle here, we have 1, 2, 3 carbons, which makes it propane dioic acid, and of course butane dioic acid. These actually have common names, and their common names are oxalic acid, malonic acid, and salicylic acid. Okay. If we're going to make a salt out of this, we used it a lot, especially when we had like acetic acid, we wanted to turn it into a nucleophile, we made it into a salt. And so what we do is we take the metal, the name of the cation, and in this case it's most of the time a metal, and we take that plus whatever the IUPAC or parent name was, and then we add 8 to the end. Imagine you're creating an ester with the metal salt. So in the case of what's here, we have a potassium as the metal cation, and then we have a propionic acid that we've converted into the propionic acid salt. So we have potassium propionate. Okay, once we get to these diacids, we actually have a lot of common names, and they're very difficult to remember. The systematic names are very easy to remember because we just have methane dioic acid, ethane dioic acid, etc. But the common names are a little bit different. We have carbonic acid, and if you think about that, that's CO2 plus water equals carbonic acid. In fact, once you volatilize it, it goes away as CO2 and water. It does not stay in that acid form. But the next acid one is oxalic acid, malonic acid, succinic acid, glutaric, and adiptic. These actually have nice and consistent names. What we can say is, if you can remember, oh my, such good apple pie, that'll get you through the first 5 diacids plus the 2 carboxylic acids on a benzene ring. Notice phthalic acid is specifically the ortho derivative, or the 1,2 dicarboxylic acid. If it's the meta or 1,3, it's called isophthalic acid. And if it's the para or 1,4, it's called terephthalic acid. And you'll see terephthalic acid used a lot because when you have PET, or polyethylene terephthalate, that's actually an ester of terephthalic acid and ethylene glycol. So you'll see that name a lot in the literature. Okay, so now let's go to esters. I just introduced you to an ester there, terephthalate. And in this case, what we're going to do is we have a carbon attached to the oxygen of the carboxy group, okay? Which means you still have your carbonyl plus an oxygen and an R group. If it had a hydrogen there, it'd just be carboxylic acid. So now we have to take the name of the carboxylic acid, and in the case of the one here on the left, we have 2 carbons in our carboxylic acid, so that'd be ethanate or acetate, and then we add whatever the other group is attached to the carbon. In this case, we have 2 carbons, so it's ethyl acetate. In the case of the next carbon, the middle one here, it's propionate, and we have the T-butyl group there, so tert-butyl propionate. If we had a vinyl group on there, this would be a vinyl acetate. Again, naming for the carboxylic acid, adding ate to it, but you still have to identify what's attached to it. So in the case of this benzoic acid, we have a benzoic acid, but we've turned it into an ester, so it's benzoate. So we have to name not only what is on the ester, so we start with that first, methyl benzoate, but we also have to label all the other things that are on the benzene ring. So in this case, it's 4-chloro or parachlorobenzoate. If we have a diacid, we use that diacid name of malonate or glutarate, etc., and we tell you what the substituents are. In this case, they're both ethyl groups. It's symmetrical, so we can say diethyl malonate. Okay, so the next thing we can do is, instead of adding an R group to the oxygen, replacing that hydrogen there, we can actually remove water from the system. And so when we remove water, we call that dehydration, or we make an anhydride. So in this case, you can imagine that if we had 1 carboxylic acid and we removed water from another carboxylic acid to create this acid anhydride and water, we would get to that material. These are commonly used. Most of the time we use them, they are symmetrical because we can't specifically pick which side is going to react with our system. And so typically we would just have to say, oh, if it was acetic acid and we've removed 1 equivalent of water, we can call it acetic anhydride. If we have a mixed anhydride, you have to state both names and place them in alphabetical order. So for example, in the one on the bottom left here, we have the acetic acid and the formic acid, so we call it acetic formic anhydride, which also happens to follow alphabetically if we have the ethyl, which is 2 carbon carboxylic acid, the methyl, which is 1 carbon carboxylic acid, so we have ethanoic, methanoic anhydride for a mixed anhydride. It's a lot easier when we have symmetrical systems like acetic anhydride because we only have to name the one side. Okay. The next thing we have is what we call acid chlorides. Now, acid chlorides is we take off the ic acid portion of it and we put ill chloride here. So in the case of acetic acid, we would take the ic off and add acetyl chloride. But of course, the IUPAC name would be the 1,2 carbons, makes it ethanoic acid. So we drop the ic acid and add ethanoyl chloride. Now, if we move on to propionyl chloride, we do the exact same thing. 1, 2, 3 carbons in the chain plus oil chloride, so it's propionic chloride. And when we have the benzoic group there, that would be benzoic acid without the chloride there. So it's benzoyl chloride. Okay. In cyclic acid chlorides, you have to actually say the carboxylic acid or carboxyl chloride. Okay, the next functional group here we're going to talk about is called the amides. Imagine removing the OH and placing an amine there. So if we have a primary amide is where you have 1 carbon bonded to the nitrogen and 2 hydrogens on it. A secondary amide is where you have 2 carbons bonded to the nitrogen with 1 hydrogen there. And a tertiary amide is where you have 3 different carbon bonds to there. Note, these are only 1 carbonyl bonded to the system. If you have 2 carbonyls bonded to the system, you actually end up with what we call an imide. So make sure that these are just regular R groups and not carbonyls. To name them, what we do is we drop the ic acid or oic acid and add amide. So in the case of acetic acid, we would go acetamide or acetamide. In our UVAC names, we would name it for the 2-carbon change, which would be ethanoic acid, and we drop the ic and add ethanamide. Now, if we have the functionalized groups on the nitrogen to be a secondary or tertiary, we actually have to note that the substituents are actually on the nitrogen. So we denote that by saying we have NN-dimethyl acetamide. That's if they're symmetrical. Okay, if you only have one group on there, you only have to have one N and whatever group is on there. So in the case of the one here on the left center is it has an ethyl group, but it still has a hydrogen on it, so we don't worry about that. But it's N-ethyl for that portion of it, and then acetamide for the acidic portion. Now, if you do have an unsymmetrical version, like a methyl-ethyl version of it, we actually will take that and use that as the alphabetical form of N-ethyl, N-methyl acetamide. Okay, now in the case of if you have an ester or an amide that forms a ring on its own, those are called lactones or lactams. So a lactone is a cyclic ester where the ester is part of the ring, not external to the ring, but part of the ring. And lactams are cyclic amides that have part of the ring. Now, if we take that primary amide we had on the previous slide and remove one equivalent of water, what we end up with is a nitrile. It's considered a carboxylic acid derivative because if we add water across that nitrile, we actually regain the amide functionality. So we have to actually think of the carbon that is triple bonded to the nitrogen as the original carbon of the carboxylic acid with the carbonyl and the OH on it. So it's used as part of the name. So in the case of this, we have ethane nitrile, or 1,2 carbons plus the nitrile. Its common name is also acetonitrile. Imagine you started with acetic acid, created the primary amide, and then took away water. That's how you end up with the acetic acid converting to acetonitrile. And then we can extend that name for other things. For example, in this case of 1, 2, 3 carbons with a double bond, so that would make it propene. So it'd be propene nitrile, or in this case, acrylonitrile. It's also used as the acrylic group, which can then be used, converted into the amide, and then dehydrated to create the common name, acrylonitrile. Okay, so the summary here is that carboxylic acid derivatives are the highest priority. You will always name them for these if they appear in your system. If you have an acid chloride, you name it as ill chloride or carboxyl chloride. If you have an anhydride or 2 carboxylic acids that have removed water, you would name that as the carboxylic acid anhydride. If you have esters, you name them for the ester with the 8 ending, such as ethyl benzoate. If they're amides, we have to show, number 1, what's bonded to the nitrogen. So we have N-methyl benzamide. Or if we have a nitrile, we name it as the functional group plus the word nitrile.